Okay, welcome back everybody. Hope you have time to digest all the information we have passed to you yesterday. So we've started from the fundamentals of a very interesting laser technique. We saw about its applications in diverse fields, and we see the details about art, minerals, industry, and a lot of robotics. We went under the ocean, under the water, and we ended up in Mars. Now I call my colleague Eduardo. We will keep going in this adventure again to space and then back to Earth for more details, technical details about the different aspects of what involves to take one of these techniques to the market. So we enjoy the workshop. Thank you.
Thank you, Pedro. It's my pleasure to introduce the last keynote speaker, Dr. Amy McAdam. I suppose this is the accent of McAdam. She's a researcher of space scientist in the Planetary Environments Laboratory at NASA. And this is part of some team of the Curiosity rover. She will give us a presentation entitled Geochemistry, Analysis in Planetary Analog Environments, included in the session of the workshop about discovery, innovation, and outer space. It's not possible to Amy to travel to Porto, unfortunately, but she was very kind to send us a recorded presentation that we hope you enjoy. The virtual floor now is for Amy. Please, you can start the video.
So my name is Amy McAdam, and I'm a research scientist at NASA Goddard Space Flight Center. And I'm going to talk to you today about geochemistry analyses in planetary analog environments. So first, a little bit about why we do field work at planetary analog sites, and there are several different reasons. So one is to study materials and processes that are relevant to understanding materials and processes on other planetary bodies like the Moon or Mars or others. And these studies can be done through in-field observations. And here, and after this and the rest of the talk, I'll focus on in-field geochemistry analyses. But this can also be done through laboratory analyses of samples that are collected in the field. Another reason that we do fieldwork is to test instruments that will be used on planetary missions, or that are like those that are used on planetary missions. And then finally, another reason that we do fieldwork is to test operations concepts that will be used on planetary missions, both robotic and crewed missions. So here I'll briefly go over the 3 field sites that I'll discuss in more detail in a little bit in this talk. So the first one is Kilburn Hole, which is a volcanic crater in the Potrillo Volcanic Field in New Mexico. And field work done at this site was done under the auspices of the Survey Rise 2 team. And I'll talk a little bit later more about what that team does. The second site is a lava tube on the Mauna Loa volcano in Hawaii. And the third site is actually several sites within the Vatnajökull National Park in Iceland. And these latter 2 sites were visited under the auspices of the NASA GIFT program. And the bottom images show examples of folks doing fieldwork in each of these 3 very interesting field environments. But before we get into the details of those field sites and what we did there, first I'll go over the geochemistry instruments. So here I'll talk a little bit about our LIBS instrument, so our laser-induced breakdown spectroscopy field instrument. But first I'll just point out that this technique, LIBS, is very planetary relevant. It's being used to assess the chemistry of planetary materials during 2 robotic missions on Mars right now, the Curiosity and Perseverance rovers. But so our LIBS is a handheld field instrument, a SciAps Z300 handheld LIBS. It utilizes a pulse 1064 nanometer Nd:YAG laser and a stacked high-resolution spectrometer within the spectral range you see there that enables assessment of most elements on the periodic table. It has a spot size of about 50 microns. You can utilize several different laser spot rasters you can see listed there when you analyze your sample. We typically average the data from 3 to 5 rasters to represent analysis from each sample. The instrument has this really interesting feature. It has a little argon tank in the handle, so you can there's an image of me on the side there using the instrument to analyze the rock. In the handle there that I have my hand on, there's a little argon tank, and when you pull the trigger to fire the laser and do the analysis, a little puff of argon purges into the space where the laser is firing. And this improves the line intensity that you get compared to operation in air. The instrument also incorporates an integrated visible camera so that you can see the area that is to be hit with the laser. I'll talk also a little bit here about a complementary geochemistry field instrument that we have, which is a handheld X-ray fluorescence or XRF spectrometer. But first a little bit about heritage to planetary science. So X-ray analyzers to assess the chemistry of planetary materials has a long history of use in planetary missions. And so there's a list of some examples there. So X-ray analyzers have been present or are present on the Mars Viking, Pathfinder, Mars Exploration Rover, Curiosity, and Perseverance missions. And these analyzers, there were a variety of different types. In some cases, alpha particles were used to excite characteristic X-rays from samples, and in some cases, X-rays. But in both cases, characteristic X-rays from the sample are measured to obtain the chemistry of the sample. But we used our handheld XRF instruments, which is a SciAps X200 instrument. This instrument enables us to assess major and minor element composition and abundance for elements heavier than sodium. And so this instrument is complementary to LIBS. LIBS can also assess elements lighter than sodium. So these instruments are great to use in the field together, and we often do that. This instrument features a miniaturized X-ray source, a high-resolution silicon drift detector, and like the LIBS, it also has an integrated visible camera, so you can see the spot that's being measured. So now I'll move into talking about field sites. So the first one I'll cover is Kilburn Hole in the Petrillo Volcanic Field in New Mexico. And here's just an image of part of the field site, sort of glamour shot. So first a little bit about the program under which this field work at Kilburn Hole is carried out. So RISE-2 stands for Remote In Situ and Synchrotron Studies for Science and Exploration. And this is a node of the Solar System Exploration Virtual Institute. And the RISE-2 effort has several themes. And one theme is fieldwork focused. And so this work took place under that theme. And the high-level goal of that theme is to maximize the science return from crewed missions to the moon by informing the best tools and strategies for those missions. And the motivation for the fieldwork, specifically at Kilburn Hole, is that Kilburn Hole is a volcanic crater in the Petrillo Volcanic Field, and it features explosive volcanic deposits that are pretty spectacular and are similar to those in the moon's Taurus Littrow Valley, which was the site of the last crewed mission, crewed lunar landing. And so the similarities between these two landscapes allowed the team to test modern instruments and CONOPS, mission concepts of operations, under conditions that are realistic as well as having a goal to advance our understanding of Kilburn hole from a scientific perspective. And so the image here shows several of us in the field using various handheld instruments to assess specific spots throughout a section in these deposits. And the LIBS is one of these that's being used by the lowest person there in the image. So this is done to evaluate these handheld or portable geochemical instruments for in situ analyses and assess the chemistry of these deposits. And the plots show LIBS data from this section as you go up section for various elements you can see there. And so these are preliminary results, and we're still interpreting them. But you can see there's quite a spread there. I pulled out sodium as a separate plot because perhaps there's a decreasing concentration trend as you go up section. But I know this needs to be looked at a little further and thought about a little further. But overall, these plots give you an example of the sort of data and trending that are possible with these geochemical measurements. So another important goal during RISE was to understand how to best use these handheld geochemical instruments during future extravehicular activities that astronauts would participate in on the moon or other planetary bodies. So having this complementary geochemical data from LIBS and XRF, right there in the field in real time, benefits the characterization of samples there in the field, and therefore it can provide really great benefits for tactical and strategic planning during EVAs. And so work on the fast data processing and visualization, to maximize the benefit from these instruments is ongoing work. But this field work under RISE 2 is helping to optimize the strategies for this. And so the image on the bottom there was made by Shreya Achilles, who's also a member of the RISE team, and it kind of shows an example data flow that is being worked on for processing this data from the handheld instruments through collecting the data, collecting the elemental data and the metadata, getting that processed to another level, and then finally getting it processed to the visualization level that would be, most appropriate, most useful for astronauts during an EVA. And then the picture there, it's kind of fun, point out. So that's several members of one of the RISE expeditions, including myself and my great lab manager. And the person that we're talking to there and showing the LIBS and XRF to is actually Jack Schmidt, who was on the Apollo 17 mission to the moon and was the only geologist to ever go to the moon. And so it was very fun talking with him, hearing what he thought about this field site, and showing him the instruments. It was quite great. And he gave us great input on this goal, right? So he had definitely had thoughts about what would be useful for astronauts to have on the moon, because he was there on the moon, and as a geologist had thoughts about what could help out. So that was really great. Okay. So our next field site that I'll talk about is a lava tube on the Mauna volcano in Hawaii. And these are some images of one of the entrances to the lava tube, both from the outside before you go in and then looking up once you're inside. So the work at the Mauna Loa lava tube took place under GIFT, which is the Goddard Instrument Field Team. And GIFT is focused on understanding the development of planetary crust and the environmental conditions that have acted on crustal materials through conducting field campaigns to planetary analog sites that enable exploration of key science questions, and incorporate instrument testing. This work in the field this field project, I should say, has also benefited from funding from the Fundamental Laboratory Research, or FLARE program, which supported laboratory analyses of samples collected in the field. So the motivation for this work is that lava tubes overall, these subsurface environments like lava tubes, may preserve records of habitability. And lava tubes have been imaged on other planetary bodies, such as Mars. And in fact, the image on the side here with the red box shows an example of a feature on Mars that we think is a lava tube. Tubes contain a variety of alteration minerals, and what minerals are present can inform the nature of fluids that interact with the tube materials. For example, the nature of the minerals can enable constraints on the pH or temperature of the fluids, and understanding those sorts of conditions is important to understanding the habitability of the environment. Microbial activity may play a role in the formation of minerals in the lava tubes, or evidence of microbial activity can be preserved in these minerals. Okay, so here's a series of pictures just quickly depicting what is required to get up there to the field site. So you start at sea level, and then in about an hour, you climb more than 8,000 feet up onto this volcano, then hike down to the lava tube and enter inside. A little more about this specific lava tube site. So this lava tube has several unique and especially Mars-relevant environmental conditions. So the lava flows that the tube is in are very geologically young, only about 200 years old. And aqueous alteration processes generally happen more quickly on Earth than Mars because there is more water and energy available. And as a result, even though Martian basalt flows are often much older than those on Earth, their general sort of alteration state can be best represented by young terrestrial basalt flows. So this young geologic age is a key aspect of note for this particular lava tube site. The young age also means that these flows are very sparsely vegetated. So this is more Mars-like, and it also reduces the chance that organics detected in the materials analyzed inside the tubes are derived from plants, which would be a less Mars-like source, obviously. And I won't go into a lot of the details of the organic analyses, but we did also perform some organic analyses of the tube materials. So it's kind of wrapped into that sparsely vegetated comment and why I mentioned that. Another unique and very interesting aspect of the environmental conditions at the site is that it experiences intermittent exposure to acidic aerosols mainly from the nearby active lava lake at Kilauea. And then finally, the lava tube is at pretty high elevation, about 8,000 feet. And this can be important because because of this, the components that make up the alteration minerals that we're studying with the in situ instruments and others are likely derived from the basalt the lava tube is in, or the volcanic aerosols I just mentioned that interact in the lava tube environment and are less likely from an oceanic source, which would obviously be less Mars relevant. And so that's another key aspect. And then also another interesting note is that this tube is near the high seas, the Hawaii Space Exploration Analog and Simulation Mars Analog Station. Chemical data from the LIBS and XRF instruments used to analyze materials inside the Mauna Loa lava tube, together with data from other instruments that we had on the expedition, which included a Raman spectrometer and also XRD data we have obtained, indicated a variety of minerals in the materials inside the lava tube. including several different types of sulfates, so sodium, calcium, and magnesium sulfates, carbonates, basaltic primary minerals, iron oxides, and also amorphous material, so X-ray amorphous material, or material that doesn't have any structural order. The comprehensive study that we're undertaking of these lava tube materials also has involved the assessment of organic chemistry of lava tube materials through Raman spectroscopy and also pyrolysis gas chromatography mass spectrometry. And in addition, we are also studying the bacterial diversity in the lava tube materials through RNA DNA sequencing. And so I won't go over the details of those results here, but all that is being worked on too. And this is ongoing work, but we expect that results will elucidate the alteration characteristics, microbe mineral associations, and microbial metabolism, with implications for Martian habitability, astrobiology, and biosignature detection on Mars. Overall, understanding the conditions for life in really young basaltic terrains like this. And then we expect this work will also have implications for studying overall potential subsurface habitats on Mars. So the last field site I'll talk about is the Hullrun vent in Vatnajökull National Park in Iceland. So this fieldwork was also a GIFT expedition, and samples collected during this expedition, lab analyses of samples collected during this expedition, were also supported by the FLARE program, as the last slide I just talked about. But I'll describe a little bit about the motivation for this specific work at this site, and then the sub-team that I was involved in at this site. Flood basalts have been documented on Earth and also on other terrestrial planets. And the flood basalt eruption at the Hullrun vent in Iceland was very well documented and very recent. So it spanned 2014 to 2015. And you can see the top image has a box outlining where that sort of area in Iceland where the Hullrun vent is. And then the lower image shows the vent and lava flow when it was active there. So this is pretty spectacular. And so the sub-team that I was involved in was interested in what alteration conditions are indicated by early alteration products, in this very young lava field, associated with fumaroles and meteoric water that had interacted with the basalt in this lava field. And so we set about using our portable instruments in the field to start trying to address that question. Okay, so this slide just shows some images of the preparation required to get ready to go out to this remote field site and do these geochemistry analyses. So it's very remote. So there's a lot of preparation required to make sure you have everything you'll need. You need to bring everything you need with you. And we camp out there relatively near the field site. So you can see here, we have our generators, we have to bring extra gas, and we have to bring all the food we need for the whole group. And you can see it's quite a bit. You can see that really long grocery receipt that Emily is holding there. But yeah, so we prepare well and then head out in our truck caravan. So we have your nice, relatively high clearance trucks here, heading out to the remote site. And this is one area we stopped in on the way. So here's a great image of our campsite, our team campsite, from a UAV that a member of our team was flying. And I'll talk about features in the sort of middle of this image as the sort of the main topics to cover for our campsite really quick. But so in the middle there, you can see there's some of them, but some of our trucks that we use to get out into the field. You can see on the left side of the image the sort of smaller individual tents the team members slept in. And then in the middle, you see those sort of 3 bigger tents, and those were key places for the team. So there's one sort of communal tent where we would have meetings or eat meals together. One of the tents was dedicated sort of kitchen tent, food tent, so where all the food was stored and all the food preparation and equipment was stored and where all the food preparation took place. And then the third one was a charging station, where a tent dedicated to charging all the various equipment we brought with us into the field to carry out our various analyses. And so we would deploy out from the campsite there to various sites, including Hollerun. And so these images are all of alteration features around and in Hollerun. And so a lot of these deposits you see are associated with fumaroles and alteration near fumaroles. In some cases, we think that the deposits are from water, like meteoric water, interacting with these sorts of materials and kind of moving them around and redepositing them in other ways. So forming in the one case, the sort of striking case in the upper left there, these sort of stalactite-like features of alteration products that have been moved by water. And so we analyzed a bunch of these types of features with the handheld LIBS and the handheld XRF. So chemical data from the LIBS and XRF, together with, again, some other types of lab analyses, including lab analyses, XRD, lab XRD, indicated the presence of several sulfates in these materials, as well as elemental sulfur. One of these sulfates was nitroalunite, which is indicative of an acidic formation environment. And then sodium sulfates were particularly abundant, which is interesting, and those particular sulfates are very, very soluble. And so this is consistent with them being early alteration products, because we would expect over time that they would get, flushed away because they're very soluble. And so this is interesting to think about from the Mars analog perspective. If these sulfates are present on Mars, they might be expected to occur in volcanic settings like this, but that were sheltered from later fluid interactions that would have, maybe leached these really soluble minerals away. If they're present, it means that there weren't a bunch of later fluid interactions. And it may be that environments like that were more sheltered from later fluid interactions are more prevalent on Mars than Earth, where there's not as much water activity. And those environments may have been especially likely in areas where there was late volcanic activity on Mars during this sort of period of drier conditions on Mars. So in summary, these discussions of examples of studies utilizing handheld LIBS and XRF analyses enable us to consider several takeaways about the uses of in-field geochemical analyses. In situ geochemical analyses assist in answering key science questions about natural processes relevant to understanding environmental and geologic history and habitability of the Moon, Mars, and other planetary bodies. Using portable and planetary mission-relevant geochemical instruments in analog environments informs the use of similar instruments on other planets, provides insight into how to best use complementary geochemical instruments to investigate these environments. And it also helps inspire ideas for the next generation of planetary geochemistry instruments. So that's all I have for you today. Thank you so much for your attention, and I apologize that I couldn't be there with you today, but I am definitely happy to take any questions by email. Thank you again.
Thank you, Amy, for a very exciting presentation and to show you the interesting aspects of the field scientist has to face to prepare to outside of this planet missions. Hope with this view you can inspire some of our younger viewers like João Pedro and Francisco, which are watching us from Algarve in Algoz, to become scientists and even astronauts. So now we go down to earth and we call Rui Martins, which is our next speaker. So Rui is a PhD in chemometrics, so he has a long experience in working with spectral complexity towards analytical purposes, so he knows a lot about these challenges in the medical field. And today he will show us some of his first insights into looking into the complexity of the LIBS signals and some of his proposals to address this problem that we have been facing. So Rui, please.
Okay, good afternoon. I'm very thankful to be here to present you something that is perhaps different in the line of the other speakers, because I am speaking about and giving a talk about information, LIBS in the aspects of information contained in LIBS. And LIBS is an information-rich technology that is not fully understood, both theoretically and both in the aspects of extracting accurate information that allows the quantification or classification of minerals and elements. So I will be covering very lightly what is the laser-induced breakdown spectroscopy and why LIBS is important for geological survey in raw materials. I will give you some examples that we have done in agriculture and geology, and then we'll go forward with LIBS signal complexity because it's a really information-rich technique, and we will review somehow what the state-of-the-art has done until today and the strategies that we are using for solving this kind of complexities of this technology, and why we think our approach is correct to achieve quantitative LIBS. And after that, we just wrap up the presentation with some conclusions. So, in a sense, and in a very precise way, LIBS is a technique where you use a laser. This laser can be in a far wavelengths, for instance, in the infrared. And if we use a laser in the infrared, we are using thermal excitation. And the thermal excitation is different from using lasers that have wavelengths that has the energy to make direct ionization of the elements. So thermal, as any engineer knows, thermal is synonymous of entropy, and therefore using thermal energy to ionize will lead to paths that are difficult because we have a lot of complex phenomena going on since we fire the laser until we watch the signal or record the signal. So the main issue is that when we use thermal energy to make ions, we first need to ablate the surface of the material that might absorb or not, and therefore, in this sense, the efficiency of ablation is very dependent on the material. So it always begins there. If the material is different, and if the laser is different, and the conditions are different, the LIBS spectra will be different. So the LIBS is a very divergent information technique between instruments and samples, because the same chemical formulation can have different LIBS spectra observed. So in this sense, I must review from an information point of view what happens in thermal excitation LIBS, and in this sense, for instance, for the sequence of events is that since we fire the laser, it occurs absorbance, and after the absorbance at the surface of the solid or other material, you have a phenomenon of surface ablation due to temperature, and it occurs in the material excitation. And from this, parts of materials are ejected, and the laser keeps coming. This is very fast. And you have thermal vaporization, non-thermal ablation, and the beginning of plasma formation at low temperatures. And this is where the molecules that are present in the vapor or in the particles begin to break down. So we begin firstly to break down the chemical bonds between the elements that make part of the molecules of the sample. After breaking down the molecular bonds, the ions that are free can be more simple ions, like small molecular ions, and as the sample keeps heating, until you only are left with elemental ions and electrons. And this is the main plasma that is formed. This plasma can have different temperatures, and in different temperatures and concentrations, very different phenomena can occur. For example, if the plasma becomes to be very dense, plasma shielding occurs, and it's not quite well effective, the LIBS. And then you continue, as the laser comes on, you continue with an electron cascade, which increases the temperature of the plasma. And with this, you can see that during this phase, you don't see very evident lines, and the lines are very broad because you have a phenomenon of Doppler broadening, collisional broadening. And the signal continues this quite continuous line, even until 1 microseconds of delay. Only after that is when you hear the shock wave, and at this phase, plasma chemistry begins to occur at the more cooler areas of the plasma. So you can see that not only physics occurs, but chemistry also occurs. And as the plasma cools down, it expands and cools down, and then it enters what we call a LIBS regime, which is the thermal equilibrium assumption, where the plasma is optically thin and we register our LIBS spectra. So you can see that until we make a measurement, many things happen, and highly complex things happened. And most of all, we are not sure how they happened, and in quantitative and qualitative ways. So LIBS is a very complex technique, where by changing all these properties along this path, the result can be completely different. For example, if we look at the lithium ores, and we have different types of lithium ores, and they will absorb more or less the laser energy, then you'll end up with different plasma temperatures. And if the temperature is low, you only will observe the lithium-1 ion lines. If the temperature begins to increase a lot, you will begin to see not only the first excitation state, but the second excitation state. So depending on the temperature, you will see there is no direct only one LIBS spectra. The LIBS spectra is a combination of all the excitation states for each element. So we begin here the complexity of this analysis. But if you continue to add up new elements, there are elements that are easier to be thermally excited, and there are elements that have lower lines, so less lines, sorry. And in this sense, when you look at a sample, you might have elements that have 1, 2, or even 3 excitation states, and some of them are not as easy to be accepted, such as carbon, that only has one observable line. So this begins to increase the complexity as each element has different ionization energies, different possible energy transition levels, and the ion populations and observed emission is very temperature sensitive. So we can see that LIBS, it has both a space and time dimension of variability. We've seen more or less the steps of the main steps of LIBS process, but it all changes in both space and time. So, for instance, as we have a temperature dynamics of the plasma heating, we will have different places where different things occur in the spot of ablation. For example, after the cool down and the recombination of ions, you will see molecular gamma emission at the border. So you are looking at very complex technique that not only looks at ion emission, element emission, molecular emission, but also recombination and gamma emission. So it's a very, very complex technique and very information-rich techniques that we must now understand and master how to remove information from here. And of course, the time resolution, you can see that in this drawing, what it tries to show is that not only you have all those ions, but you will have, depending on the thermodynamical, chemical energies and kinetics of reaction, you will have this kind of plasma reaction network that you will end up with different molecular lines seen and element lines seen, depending on the type of the chemistry of the sample. So LIBS is not only elemental; it has all these kind of complexities, and it is not very easy. Although all those lines seen there are not very easy to understood, not in complex samples. The theory of LIBS, the theory of LIBS is governed by equations that are well known to science. These are the plasma equations, also known as the Saha-Boltzmann equations, and data for all the elements and ionization stages can be found at the NIST element database. And you also can find for different elements at the other LIBS databases some LIBS spectra for each element. But of course, if you change the conditions, all the observed spectra, you have to be careful using this, because if you change the conditions, all the LIBS spectra can change a lot. So a word of caution here. You can also find online a Saha-Boltzmann simulator at the LIBS database from NIST, where you can make your own recipe in percentage of elements. But this is only a theoretical, very simple theoretical simulation, where you are only assuming that there is no reaction, no reabsorption, whatever. So you are assuming that this is a mixture of ideal plasma. But this is where engineering enters. In engineering, we are able to use methodologies where there is still many unknowns. So in this case, we are using chemometrics and machine learning to try to figure out and unscramble the information from the LIBS spectra, which is highly complex, and try to figure out how to use the information to quantify, for example, in this slide, the lithium quantification from exploration drills in Barroso mines here in Portugal. And you can see that the information with some methods that we developed have quite good accuracy in quantifying the lithium without a lot of sample preparation. But in another way, we can make also classification, and try to understand what kind of minerals are in the sample. And from this type of mineral or ore, we can understand the typical composition. And for those, as you've seen, for this kind of portable LIBS systems, this is like an intelligent or expert system for discovering or telling the user what type of mineral he's looking at. For example, we have been using this in that robot that we have here at INESCTEC, and with field, that robot is equipped with spectroscopy, but not LIBS spectroscopy. We took samples to the lab just to make sure that if the LIBS is in agreement with other instrumentation that we used in the field. But in here you can see that we used LIBS to characterize the nutrient uptake of different tissues in a vineyard, in this case in grapes. And we were able to identify some micronutrients and macronutrients, and not only identify these states as these accumulate in different quantities in the different tissues. And for example, with this kind of approach, you can see that until the harvest, for instance, the pulp accumulates calcium ions, and also nitrogen, and some magnesium. So we could see this is an important application because these methods for agriculture are quite important for managing the nutrient uptake of plants for the correct use of fertilization, but also agricultural practices. And with this kind of approach, we can make maps of nutrient absorption for precision agriculture. In another example, we took this LIBS that we developed at INESCTEC, and we took it to a kaolin mine, where it was possible to use the LIBS to make kaolin grading the quality of the kaolin. But as we had also a library of minerals, we were able, for example, to discover an unknown sample, this black rock, that was identified by our library first as a tourmaline containing lithium. And this was a surprise, but also afterwards confirmed by the geologists. For example, we also make geological survey maps. We can scan the surface of rocks for elements and then make this kind of images. For example, here for iron, for sulfur, calcium, and other elements, and check their qualitative distribution. Or we can make models quantitative models to go and quantify the different elements in the different parts of the rock. In this example, this is a mica sample that the geologists in the University of Porto found that they have lithium, and the lithium is only separated by an abrupt interface, where we can see that very clearly in the LIBS signal. This example is the most important to show the potential of LIBS. This is because, as you've seen before, LIBS not only has element information, but has molecular information. And in here, we are looking at using the LIBS to try to give a probability of showing a spodumene mineral in a sample. And as you can see, there is a spodumene vein here, this more whitish part of the rock. And the classification models are able to predict from the LIBS signal where the mineral is. So this means that the end result or the end signal of LIBS has some kind of structural information from the initial breakdown. So, and this is really relevant for geology because not only you are quantifying the element, but you are trying to classify in real time the type of mineral that you're looking at. In this example, we made the quantification use, as the last presenter showed. They used the commercial equipment Z3000 from SciAps, and in here we tried to quantify the lithium in samples from Barroso with this equipment. And this equipment was tested against the laboratory ground truth method, which is ICP-MS. And these quantities were used to supervise a model, a quantification model, a first quantification model with that data augmentation techniques that allowed us to obtain a 15 to 20%. But this means that this equipment in this kind of samples not only is capable of classifying samples, but having a semi-quantitative and qualitative quantification of lithium, which is very important for prospection. In this example, we have the same samples, but we use the laboratory LIBS that we developed. And of course, as it has more channels, this means more spectrometers, more resolution, and also a laser with much more power. The results are much better. But the information, this means the information is there, is the same as SciAps, and laboratory or more powerful lasers or more powerful equipments will have better results, just because the information has less noise, and the information of the LIBS spectra is more sensitive. So after these examples, I would like to go through some the main difficulties of processing LIBS spectra. One of the most important ones is that we cannot assume that each line that we observe in the LIBS spectra belongs to a single element. This is because there is a thing that is called interference. This means that lines that are very proximal are seen in the same pixel of the CCD, or in a very nearby pixel of the CCD. This is CCD. And there is also the problem of line broadening, which means that each LIBS signal has uncertainty in the lines due to the plasma process and not due to instrumentation. So you have uncertainties in the line position, not only due to the instrument, but also due to the plasma. And here, for instance, for the case of lithium, you can see that as we increase the plasma temperature, interferences between lines begin to increase. And as interferences between lines begin to increase, you get more, it is more difficult to use the lines of lithium solely for lithium quantification. And this takes us to the state of the art of using the Lattice-Boltzmann equation to a method also known calibration-free methods. Calibration-free methods would have the appeal to not have to use laboratory methods to calibrate, because you would use the LIBS theory or plasma equation theory, not only to first simulate the spectra, because you can simulate the spectra. As I've shown, NIST has a LIBS spectra simulator, but you can do the reverse engineering or inverse method, which is known the calibration-free method. This calibration-free method is a reverse engineering problem where we try to optimize not only the plasma temperature and electron density functions after the line identification. And here you start seeing big problems, because the first thing is, what is the line identification if I have a complex sample? So line identification in complex samples is difficult to make and difficult to estimate. And after that, as you make these kind of mistakes, of course, your estimations of the temperature and electron density will never converge to the correct value. And then you are starting to have a very computational expensive method to try to compute the element's concentration. So you can see that the forward problem is very efficient, very easy to calculate, but the inverse problem is very complex to calculate, and as the equations do not translate the total reality, these methods are appealing, but they are not realistic. And they cannot be used for geology because geological samples are highly complex. For example, just to show you a counterintuitive example of how complex this is, from the lithium drill, you can see that although the first 40 meters of the drill have almost no lithium, the lithium lines are higher in this region than in the spodumene vein. And this is really counterintuitive. So how is this possible to have a higher intensity of lines in lower and very lower quantities of lithium? So this happens because of the natural distribution of the geology. Spodumene is associated with quartz crystals, and the quartz crystals and spodumene not only are hard, but they absorb much less the laser. And the plasma efficiency of both breaking down quartz crystals' molecular structure and the absorbance makes that the signal within the spodumene vein is much less sensitive to the lithium emission than the first part of the drill. So this is a perfect example where the theory that we have about LIBS will never work at this stage because we don't have all the knowledge to simulate or to make an inverse problem to solve this kind of observation. Also, we tested, for example, state-of-the-art machine learning techniques and chemometrics, and you can see that for both convolutional neural networks or deep learning networks or artificial neural networks, or even k-means clustering or similarity, as we see, and partial least squares, which is one of the most popular chemometrics algorithms, they perform poorly with this kind of data. So in this sense, we don't have, from the state-of-the-art tools, they are not adapted to the complexity of LIBS. And for this, we must develop the new ways to try to process the LIBS information and its complexities. So another problem that we have is this one. LIBS is a high-throughput technology. We can fire the laser as many times per microsecond and have thousands and terabytes of data from LIBS. But the main issue is we don't have a correspondence with laboratory data. And as we need laboratory data to calibrate the LIBS, we have a problem known as data scarcity. And as people that work in machine learning know that you'll need significant amount of data to have a data-driven technology working fine. So data scarcity is a big problem for geological LIBS. And we are trying to address this issue by developing methods that can augment the data. Of course, these methods are not equal of image augmentation as many algorithms exist for deep learning, because we need to respect the proportionality between the LIBS signal and the concentrations. But this is one of the big problems because ICP-MS, for instance, which is a ground truth method, is a very expensive method. So in this sense, we are developing our models, which are local models. What do we mean by local models? We mean that within samples that have different characteristics and different type of LIBS characteristic spectra that will cluster together, will have properties that can be used within this kind of clusters to quantify the elements that we need to quantify. So in this case, these kind of methods are agnostic to the data set and allow the human interpretation because we can understand what lines are being used for the quantification. And somehow it has been one of the most effective ways for quantifying from data from Spectra since 2006. So there is a gap that although many methods have appeared, since 2006, this method has been in complex samples one of the best methods to work out. And this also has links to the spectroscopy theory, at least because we can understand that there is a direct relationship between concentration and the intensity of spectral lines. So this is much more technical part, where from a PCA space, which is a variance space, we try to get the most similar samples. And from these samples, we try to maximize the covariance between the LIBS information and the sample composition information. And this is made by a local partial least squares. And one good thing is about partial least squares is that if you only use one latent variable, which means that only one dimension, it means that you are using the direct information from the LIBS spectra. And in this sense, this is the ultimate goal that would like to seek, because you would find a covariance mode in your data. You would find a group of samples that have a direct relationship between the lines interferences and the quantification. But you can, if you don't have enough data, you can optimize from 2 to 5 latent variables to get the model. But more than 5 latent variables is very difficult to interpret and to have a human interpretation of the results. And somehow we are not going to use this, even models that can be statistically relevant. They are not quite understandable for human reasoning. So with one latent variable I was talking about, as there is the direct correspondence between the spectral lines. Not only we have a statistical validation, but we have a causal validation, and this is crucial for quantitative LIBS. Because, for instance, if you are quantifying an element, but the line elements are not there, you have to inspect why you are really quantifying it. So the lines should be there and should be non-negative. And if the lines are, if the coefficients are negative, you should also understand why they are negative. Why are there some kind of interference that make them negative? So it's crucial to make this causal interpretation to see if the models are correctly identifying the information content of the spectrum. So in here, I am using solely the data. This is data augmentation, solely the data of the data set. Of course, the result is not as semi-quantitative, not very good, but you would have some semi-quantitative quantification. But when you make random combinations of the spectrum and the chemical composition, you can make data augmentation, and of course you start getting more accurate results because you are finding groups that are have more covariance, consistent variance. Well, if we do this with our laboratory LIBS, then you can see that the augmented data is much more data than the real data, and that this data already have some direct correspondence in the two clusters to the lithium line. Of course, lithium lines, of course, it's with high dispersion, But then when we use local models, then we have this kind of quantifications. And this begin to be quite good. So with a very good limit of detections and error percentages. So to end my presentation, LIBS is an information-rich technique, and the main problems that we face are, which are known as matrix effects, interference, and the plasma dynamics, which in plasma dynamics is not only the physics but the chemistry. And some solutions that we are working on is both pre-processing and performing local search in the feature space. Preferably, if we find covariance modes, we are very happy about it. So the challenge is that this problem, the main mathematical challenge is that quantifying the covariance solution is that the solution is non-unique. But there is only one locally orthogonal solution. What does this mean? It means that there is a solution where the variance is explained only by the lines that are correspondent to that element. And this leads us to the development of a method that will have a causal interpretation and not only statistical validation. So this was my presentation.
Thank you. So thank you, Ruud, for navigating us through the complexity of the LIBS signal. You have someone has question for Rui? So Rui, you showed us some of the reasons behind the complexity and some of the ways to address it, and you show us that the capability to interpret why the models are going one way or another is important to optimize the data. Now, considering what we've seen and our goals in the project, I ask you, is it possible then to, when we reach the step that we leave this into a machine and the machine can itself start to use this information to take decisions? And so how can we automate this? Are you optimistic about this step that is missing? Or?
Well, as I don't know, but if you know, Professor Ramos Bro, which is one of the founding fathers of chemometrics, published last week a paper where for complex samples, human interaction is always important. So at this stage, in the development of this kind of models, as the data is very complex, it's important to have an chemometrics expert to validate the existing information. Once you validate existing information and the information space is validated, then you can automate. Of course, using methods where you can interpret the data, not only black boxes as artificial neural networks or deep neural networks or sport vector machines or other state-of-the-art method, you can analyze the data and understand why they fail. Because model failure is not bad, it's a good thing, because if we understand why the models are failing, we can take corrective actions. If we have methods where we don't have ways of diagnosing why the models are failing, we cannot, or we are like working in silico and not working smart, trying to develop methods that are able to use human interpretation to improve them.
Okay, thank you. Any more questions?
I have one question. Statistically, I understand the identification or the quantification take into account the deep learning. I don't understand if it is possible to have a causal interpretation with deep learning, because with the causal interpretation, I need to have some dynamics in things. And not statistically, the spectrum is not statistically equal to another spectrum. Introduce the causal interpretation in deep learning is what is the way to introduce causal interpretation in deep learning?
To me, it's hard to introduce, because when you do convolution, in spectroscopy, we want to avoid convolution, because convolution averages everything, and then you are losing interpretation in the different layers. And as As the non-linearity of many type of samples, you have to increase the number of layers and the number of convolutions, steps, and then you begin to be very difficult to interpret what each of those layers, for instance, until after the third layer is doing. So this is why, not only because of the results, because deep learning methods need much more data than this kind of local methods to work, but to interpret them is very hard when compared to interpret the linear relationships from lines and concentrations.
If I relate my question with the question, to automatize the process of the identify and quantify the material, if I understand, the solution is open. It's not infinite, the solution, but no. I can have 3 or 4 possible identifications. But why we don't build a new level of the interpretation? And you in the identification and quantification, you open several solutions because the solutions are open, and you, after another measure, you start to dismiss some possible solutions because it's not more compatible with the next steps. And after some times, maybe I have the convergence for one identification or...
But the problem is data scarcity, because we need the ground truth data to confirm and to train. So to get that, as is very expensive, to make a database of 10,000 samples, we either have...
But it's not possible to have artificial synthesize. You can synthesize a spectra.
Yes, that's what we've done. But the problem is that we are not in total control of the theory of synthesizing synthetic spectra. And that's, of course, a challenge. And one of the challenges of LIBS is exactly this one, is from data scarcity.
Okay, but after sometimes in the same mine...
Exactly. After, if you go to a mine, for prospection is more difficult. But if you go to a mine where they have to resample each day, then it's okay.
Just, I think, José, some comment, question?
Yes. It's more a philosophical comment and question at the same time. Assuming that when we are hitting our sample with a laser and every single shot will be different, only with a few exceptions that you could be working with a, let's say, a pure copper, but even in this case are difficult, that the amount of mass that you ablate per pulse is different, that the amount of the photons that you generate related to the the mass ablated is completely different, so on. So at the end, how good do you want your method to be happy? Because maybe we have to admit that the technique reaches a point at that sometimes the variation of the technique is reflecting the variation, the heterogeneity of the sample.
Yes. Well, to address that, what we do, and we are making it a project, and in another fields that I work in spectroscopy, we have to have the best synchronization as possible between the sample measurement and the chemical measurement, the best as possible. But as you are saying, and in your presentation, for instance, if the variability is to the nanoparticle level, then of course our representativity is an average representativity. So we must be happy with that kind of limit. It's a limitation of the technique. So, but if we go to, for instance, 10% of mean average percent error, we can consider this a very good technique for quantifying in situ or something like that. But of course, we will never go to errors such as mass spectroscopy or any other method of some sort that is in the lab. But these kind of approaches are not totally meant to be in the lab. Perhaps in the lab, if we control the sample heterogeneity, of course, we can go to very low quantities. But perhaps for mining to go to 300 ppm is already a very good limit of detection.
You know, I agree. I agree. There is a limit. It has to do with matrix effect, where you can't do anything against that. It doesn't really matter how much maths do you apply that. But even in wet chemistry, with a regular ICP, limits of detection without an internal standard better than 5%, you don't get it. And we're talking about a wet chemistry with a dissolved sample. That is the easiest way to analyze something. So 10%, honestly, I will buy it.
Yes, that's
easily.
I think if you respect the limits of detection for the threshold of decision of any area, then of course you have a very excellent instrument and a very excellent way to work in the field, or even with some sample preparation, for instance. So that's a very good instrument, because the alternative is the low throughput in the lab. So that's it, I think.
Okay, so thank you, Rui. Thank you very much. So our next speaker is Feven Desta. She's also from Technical University of Delft. She's a member of Project inSITE. So I take the opportunity to thank all her efforts in trying to address this problem. She's working together with Rui and Goratz to try to have this challenge of addressing the sample ground truth against the LIBS signal in some efforts. So Feven is a geologist, and she has a PhD in geoinformatics, and she will be addressing this topic in their talk. So Feven cannot be here with us, and she was kind enough to make the effort to have a recording of her presentation, and this is what we'll see right away. So thank you, Feven, and so please.
Good afternoon, everyone. I'm Feven Desta from Delft University of Technology. This presentation is to give you a short introduction to our research work in the section of resource engineering at TU Delft. The title of my talk is Technology and Advanced Data Analytics for Raw Material Characterization. The study involves technology and data analytics to generate information on the key geological attributes in mining, and also in different geological studies. Before I start my presentation, I would like to show the outline of my talk. First, I will start with some general information on the use of sensors and the data analytics. Then I will introduce you to the test cases. Following this, I will quickly go through two of the results in our research. One is part of the real-time mining project, which is funded by the Horizon 2020 program. This project is completed. And the other example is part of the inSITE project, which is funded by the EIT Raw Materials. And this project is in progress. Finally, I will conclude by addressing some of the outputs of our research work. Why we need minerals? This is an interesting question. Our day-to-day life is highly linked to minerals. For example, we need minerals to build a car, a smartphone, laptop. We can say almost everything around us is made of minerals. Moreover, climate change is a big concern that needs a green energy transition via clean energy technologies such as solar panels, wind turbines, and electric cars. And the deployment of clean energy technologies requires more minerals than their fossil fuel-based counterparts. For example, if we compare a typical electric car with a conventional car, the electric car requires almost 6 times the mineral input of a conventional car. So attributed to the population and economic growth, and also the need for achieving the green energy transition, there is an increasing demand for minerals and mine products. Okay, there is an increasing demand. So what is the cost? What's the concern? The increasing demand shows greater prosperity. That's a good thing. But it also leads mining to the extraction of materials in geologically complex regions. These regions can be exemplified by a low ore grade, deposit at deeper depths, low continuity. So mining in these areas is difficult since it requires more time and resources to extract, process, and market the mined products. So the process becomes slow and complex. Now it triggers another question: how to ensure sustainability in supply? How can that be achieved? In our research, the proposed approach is as follows. As I have mentioned to you earlier, the increase in demand shows prosperity, which is a good thing, and also leads mining in geologically complex conditions. And this requires novel technologies and rapid data analytics. So innovative ideas are required for the simultaneous development of technology and also data analytics approaches, so that could potentially lead to automation and digitalization of the mining process. Through data analytics and sensor technology, we can achieve automation or digitalization of the digital transformation, which likely results in resource efficiency and also sustainability in mining to ensure prosperity in return. For example, technologies can allow the exploitation of new deposits in more complex scenarios, or it can also be, technology can also be used to upgrade the already existing low-grade mines. So it can potentially result in resource efficiency. This is a schematic representation of the electromagnetic spectrum. It is the range of all types of electromagnetic radiation and their respective wavelengths and photon energies. As you can see from the figure, the electromagnetic spectrum is subdivided into regions, different regions, from high energy zone to low energy zones. And there are sets of sensor technologies that operate over the different parts of the electromagnetic spectrum and measure the different material properties. For example, if we take X-ray, it's used in the airport and also for medical examination. And the infrared, they can be used for mineralogical studies, for analysis of minerals in different materials. So in our section, we use technologies including RGB imaging, visible near infrared, shortwave infrared, midwave infrared, longwave infrared, Raman, LIBS, and XRF techniques. And we use these technologies to generate information on the key geological attributes, such as mineralogy, geochemistry, fragmentation, or geometry. Sensors produce data having different natures. They provide multivariate data, and it's difficult to understand by visual inspection or intuition. For example, if you see these two data sets, this is the example from mid-wave infrared. Actually, the mid-wave infrared data has more than 5,000 variables, and this shows only a small part of the data. And this is hyperspectral image that provide both spectral and spatial information. But just by looking at this data, it's difficult to tell what's inside in this data, what kind of information we can get from this data. So we need data-driven approach to extract useful information out of these complex data sets. This data-driven approach could be the data mining techniques, the machine learning techniques, chemometrics, and also it's very important to consider the signal processing techniques to enhance the signal to noise ratio or to avoid or minimize the noise in the spectra. So we can use sensor coupled with data analytics to generate knowledge. But the question is, can we maximize the results? Can we improve the results? And the answer is yes, it's possible to enhance the information from sensor data using sensor combination. And sensor combinations can be applied using different approaches. One is using the sensor physical integration, but this is expensive and challenging in practical implementation, especially for those sophisticated techniques. And data fusion can be an alternative and economic option. Data fusion is integration of different sensor outputs into the same model. So the synergy between data blocks can maximize the accuracy of the models. It could be classification models or prediction models. So sensor technology, I mean, the data fusion can improve precision, reduce uncertainty, improve availability and accuracy. So sensor technology coupled with data analytics can be used to characterize material at different levels, from identification, classification, and quantification. We have different test cases. This is one is the Reiche mine, which is located in Germany. The area is characterized by event type mineralization formed by two hydrothermal events. The typical minerals are the sulfide minerals, such as chalcopyrite, galena, and sphalerite. And also we have samples collected from different deposit types. For example, we have lithium ore samples, bauxite ore samples, and different other samples from different deposit types. This gives the opportunity to investigate the usability of technologies in different material mixtures. So different methodological approaches were developed to extract information from different sensors. Individual sensor technology were assessed, and data fusion was implemented at different levels to see the performance of the individual techniques with the fused data blocks. In this presentation, I will show you two particular examples. The first one is the fusion of mid-wave and long-wave infrared data for quantitative analysis of minerals. The second one is the use of LIBS data for the identification and classification of materials in different deposit types. The second one is the work is in progress. I will come to it later. First, let's see the outputs or the results from the first application example. Infrared technology is one of the well-established techniques. It's a mineralogical technique that provides information on the functional groups. The technique can be used for identification of a wide variety of minerals. And commonly, it's used for qualitative analysis of materials here. And accurate quantitative mineralogical data has significant implication in mining operations and also in any geological studies. However, quantitative analysis of minerals is challenging for most of sensor outputs. And it requires advances in data analytics. In this study, the aims of this study are twofold. One is to investigate the use of mid-wave and long-wave spectra for the quantitative analysis of minerals in polymetallic sulfide ore samples. The second objective is to evaluate the data vision methods using linear and nonlinear multivariate regression techniques. This figure shows the workflow diagram depicting the steps applied for the data fusion approach in this study. First, data pre-processing techniques were applied for the 2 data blocks, and 2 data fusion approaches were applied. One is the low-level fusion, and the second one is the low-level fusion with feature selection. The first one, the fusion was the entire variables in the mid-wave infrared and long-wave infrared data blocks were concatenated after pre-processing. However, the second one is based on feature selection or extraction. So this approach can allow all non-informative variables to be removed in the feature selection step. The approach is not a standard mid-level fusion, because in mid-level fusion, a modeling step is required for the extraction of the informative features. However, the feature selection method deployed in this study was not based on model outputs. Instead, mineral library or reference spectra were used to identify the wavelength location of the spectral features corresponding to the functional groups of the target minerals. So for this approach, the hypothesis is that variables that correspond to the main spectral features are the most informative or important for the prediction of mineral concentrations. So relevant information were extracted from the 2 data blocks separately. Then the extracted features were concatenated to form a single data matrix. Then prediction model were developed using the fused data blocks and different models. Then once the models were applied for individual and fused data blocks, the results were compared to see if the prediction accuracy is improved after data fusion. And the result is, of course, validated using the independent data sets. This table shows the results of the mid-wave, long wave, and low level with selected feature data blocks. As the experimental results shows, the mid-wave and long-wave infrared data sets include relevant information that can be employed in determining mineral concentrations. Moreover, data fusion significantly improved the model prediction accuracy, as you can see here. Models, comparing the model using the linear and nonlinear technique, yeah, it shows some variation, but all in all, we can say the result is somehow comparable. So although the acquired prediction accuracies are lower than those of the standard laboratory-based techniques, we believe that the proposed method is suitable for rapid in situ indication of mineralogical concentrations along the mining value chain. The other example is the use of LIBS data for the indication and classification of materials in different deposit types. As I have mentioned to you earlier, this work is in progress. LIBS is a rapid chemical analysis technique. The technique can be used to characterize a wide range of material. It's mainly used for identification of elements. However, as it is the case for most of other technologies, quantitative or semi-quantitative analysis of elements using LIBS is challenging. So the aim of this study is to investigate the use of LIBS for the identification of elements in different material mixtures. And the other objective is to assess the possibility of classification of materials based on the elemental concentrations. For this study, the LIBS data were collected using the IRIS spectrometer at Spectral Industries Laboratory. After the LIBS data were collected, data pre-processing techniques were applied to minimize the noise in the spectral data. Following that, LIBS spectral databases and published results were used to identify peaks that correspond to the elements of interest. Accordingly, the target elements were identified in most of the analyzed samples. Following this, following the element identification task, the possibility of classification of samples based on the concentration of elements was assessed. And this classification work was optimized by selecting a different peaks combination. And it's observed that the choice of peaks has influence on the classification accuracies. This figure shows PCA model for the classification of the samples, the analyzed samples using the classification of the samples based on the concentration of copper. This is, for example, the classification of the samples based on copper concentration, and this one shows the classification based on lead concentration, and this one with the zinc concentration. And once the important peaks were identified based on the material matrix, classification models are being developed using the linear and nonlinear classification techniques. And these experimental results show the possibility of classification of the materials based on the elemental concentration. This work will further be extended to investigate possibilities for semi-quantitative analysis. And this work will be done together with the team at INESCTEC and the Geological Survey of Slovenia. And finally, the output of the project will be used to develop database for online in situ analysis of material at different levels and in different harsh environments. Before I finish my presentation, I would like to mention some of the results of this research. Usable results were achieved for the identification, classification, and semi-quantification of materials using the infrared and other technologies. The mid-wave infrared and data fusion allowed increased accuracy compared to the individual data sets. And the mid-wave infrared is used for the characterization of materials at different levels. This is interesting since mid-wave infrared is the least explored region of the electromagnetic spectrum and the least explored region of the infrared due to limited historical sensor development. But the results in this research suggest great potential of the technique in material characterization. The experimental results also show that LIBS spectra can be linked to the elemental concentration, and promising this. The result is promising for semi-quantification using optimal methodological approaches. With this, I conclude my presentation. If you need further information, please feel free to contact me via this email address here. Thank you for your attention.
Now we have our final presentation. This one I think will be presential. It will be shared between Kanaki Pondicherry and Mauna, both from Ghent University. And they are working also in inSITE project and addressing two also very critical aspects that sometimes are not seen by when you see a final product, which is optimize the behavior of the materials. And this is the role of Kanaki. She has a PhD on material science in these aspects of tribology and all the how to optimize materials to work in these very harsh environments. And Manjunat is also expert in design of mechanical engineers and find ways to make these systems work for a long time and repetitive cycles. So we will find some interesting information. So please.
A very good afternoon to one and all. And I'm Kannaki Pondicherry, and together today with my colleague Manjunath, I'm going to give you a brief introduction or an overview of who we are as researchers or as a research group and what we do, as well as what is our role in inSITE in this project today. So we are going to talk about durability, materials, and wear mechanisms, the topic which is far away from the plasma, the radiation, the quantification, and the other aspects that have been spoken about in the two-day workshop yesterday and today. So who we are the laboratory of Ghent University, Belgium. This is a laboratory, so here you can see huge amounts, large-scale test rigs. So here we have a lab where we together shared the space with the construction department, but this is on the right side, our laboratory, where we have large-scale test rigs as well as small-scale test rigs, and we have modular instruments, and we as an engineering group, we design machines and we construct test rigs that are custom-made to solve the problems of the industries. So to give you a brief overview of what is our research area or the research expertise that we have in our lab, we work in fracture mechanics, the field where people like to break things or probably tire the material for such long times that they break by themselves. So the second field that we also work with or have an expertise in is tribology, the field which I come from. So tribology is the study of wear, lubrication, and friction. I would also introduce or give deeper or larger overview in my coming slides. So what do? We do small-scale testings as shown in these figures, where the sample size can range from 4 millimeters in length and 5 millimeters in thickness, and loads of 0.5 to 1 newtons, to large-scale test rings, where we have a bearings of 400 mm in dia, which is the real-scale bearings that are used in water gates in Belgium to close and open whenever there is a flooding or water levels rise. So these large-scale test rigs have a load range of 1,500 kilonewtons, and that's the scales of loads we work in. We also do experimental investigations. Like I said, we try to break things so they pull or compress, and that's how they work with materials. And the second, we also are extensively working with finite element modeling, both in the fields of tribology as well as fracture mechanics. We are also involved in computational studies using molecular dynamics, where we study the interaction of molecules with lubrication studies. So that's also an expertise that we have in the lab. So we are a research group of 5 professors with more than 30 PhD research students of international background, and that's the research team of our group. We are also an industrial service. As I already mentioned, we cater specifically to the problems that are brought to us by industries of the real applications and give them tailor-made solutions. So, coming to again, to give you a deeper overview of what is tribology. So tribology is the study of friction, wear, and lubrication. So where do we see them? So the background picture that you see involves all three basically. For examples, when you want your cars to run smoothly, you do not want friction or the components to wear off or break. So how do we do that? We use oil and we reduce this friction or wear in components. Now, if the oil is too viscous, the gears do not move, there is high friction, so your cars don't probably work. But when the friction is too low, there is also another problem where gears come into contact with each other and they wear. So not all the times friction wear and is, let's say, negatives. There's positive effects of these as well. For example, the friction is necessary when you walk on the floor, as well as wear is necessary when you want to machine a component. That means you want to cut a sample or you want to make specific shapes of the samples. So from these fields of tribology, how are we involved in this project of inSITE? So we have already heard a lot about plasma, the ions, the quantification. We have heard about the minerals, the geological part of this project. But right now, we are going to deal with a very small, probably a minute part, that is the casing of this LIBS. You have the electronics, you have the mechanical components, you have the cameras, the sensors, everything. But they have to be encased in a system that is both basically working in harsh environments. When I say harsh environments, it is the sea, the interaction with the minerals or sands, or definitely the pressures. So that brings us to our role in this project, where we are involved in the material selection of the housing as well as the mechanical design. So I'm being a material scientist, I'm involved in the material selection, and later on in this presentation, my colleague, a mechanical engineer, will tell in detail what is the process of the mechanical design that we approach in this project. So what are the two primary criterions that we look at from a materials point of view? The first primary criterion is the mechanical strength of the material to withstand such high pressures. And the second is the tribological, that is when we have harsh operating environments of the sandy environments and the corrosive seawater environments, we deal with the tribological aspect of those studies. So to give you a very probably basic things that we material scientists look at is the diagrams, where we look at the properties that are of interest to us. For example, in this case, it's fracture toughness and strength. And then we see the family of materials that are actually usable, and depending upon our thresholds, we select the group of alloys or group of composites or polymers or materials in general of what could be potential or candidate materials. So from this literature piece, we have shortlisted five materials. Those are polymers, aluminum alloys, high-strength steels, titanium alloys, and composites. So then we had a brief literature dive again, and we had a look at what depths do these materials actually operate at. So for example, if we have aluminum alloys, they operate at 700 meters of depth, whereas stainless steel operates at 4,000 meters and titanium alloys operate at 6,000 meters, whereas plastics are not so, let's say, reliable in higher depths. They only are limited to 200 meters in operation. So the goal in this project was to aim to a depth of 2,000 meters. Therefore, we tried to do a study based on these three materials, and the potential material probably would be the stainless steel. Yeah. Now coming to the tribological aspect, so why tribology is because whenever you take any kind of offshore working environment, whether it's underwater or, for example, dredging, which has also been spoken of, or shipping or mining, in any of these components, there is always interaction of, or there is always inclusion of harsh environments. So you have the corrosion and you have the abrasion because of sand. So what are the, so coming to the words of abrasion and corrosion, most of the people get confused. So let's just, and there are a lot of types of wears, because each and every application that I've showed in here has different types of wear. Wear is a family of, let's say, maybe 27 types of wear, but to give you a brief overview, what is wear and what are the types of wear? So here I have, so wear can be classified majorly into 4 different types. One is abrasion, then it's erosion, adhesion, and fatigue. So where do you see them in real lives? Abrasion is nothing but sliding of two different materials against each other. And yeah, probably you might have seen it here, if you have a pet, probably. So where do you see erosion? What is erosion? Erosion is the impact of particles or molecule or fluids at very high velocity, extremely high velocities in meters per seconds. And that is probably seen usually in the pipes where they try to pull in the ore or the sand and dredge. So that's erosion for you. Then we have adhesion. Adhesion is where two surfaces slide against each other. But the difference between abrasion and adhesion is that here, in this case, the material sticks and then removed. So this is a difference in mechanism, and we see that in our daily lives in this example. Fatigue is again where we have repeated motion on a particular substrate, and there we have the examples of rails, where you have the rails that are being worn out because of continuous operation. Now I'm going to focus more on abrasion because that is the phenomena that we probably expect that might happen in the contact of sand, water, and in case of LIBS. So coming to what is corrosion in that case, because tribocorrosion is an amalgamation of two words, that is wear and corrosion. Corrosion, in fact, is an electrochemical process. So it's not let's say not physical like abrasion, but it's an electrochemical process, and you often see rusted parts. To give you a schematic overview or a brief recap of what is corrosion, so here we have a steel substrate. So this steel substrate, whenever it comes into any kind of medium, it can be air, it can be water, it can be any kind of fluid. So it forms a passivation layer. For that matter, any metal or any kind of two environments that come together, they have a reaction between each other. This was specified yesterday because the statues or the chemical composition that was being analyzed of the bulk alloy has been done at the depths and not at the surface, because there's a lot of chemistry that is being going on here. So when we have a passivation layer, of course, there's a, how does this form? So here what happens is whenever they come into contact, there is an equilibrium that's being established. So this happens. So you have iron. So the iron ions are, let's say they are ionized, and we have the electrons here. Because of the difference, they move to the other position. And then here, oxygen reacts with these electrons, forming hydroxyl ions. And these hydroxyl ions then react with these Fe3 ions that are formed and finally giving rise to dust. So this is an electrochemical process that is happening here. Now, what is tribocorrosion? So as I already mentioned, it is the amalgamation of two words. So also it's the interaction between three basic components. So it can be steel reacting with sand and water. What happens when these three come together? So this is wear and this is corrosion. Now, ideally, everybody wants to quantify things. This is not a qualitative analysis, because we always want to quantify and we want to understand the influence of each other, basically, and also give them some numbers that mean something. So how do we do that? So ideally, if we assume wear to be some 10 units of material loss and corrosion to be some kind of 4, and when we have to total it, it should be 14. But this is an ideal case, and in the world, it's never ideal, so we never have these kind of results. So what we have is something extra. It can be either plus or minus. And what is this extra called? It's called synergy. So this synergy arises because of two reasons. So one is when we have steel and seawater, as I already mentioned, we have a passivation layer forming. That depends, the plus or minus depends upon the nature of this passivation layer. If the passivation layer is strong, abrasion resistant, and adherent, then we have coupling with, and on coupling with abrasion, then there is no wear. That means you will have a lower mass removal on coupling, basically. On the other hand, we have the second option where we have the material that can be, or the passivation layer that can be easily abraded, weak, or non-adherent. What happens in that case? So as the layer is weak and non-adherent, and as the abrasive moves over that layer, you have more surface that is being exposed, corroded, and then again abraded, being a cyclic process. So what happens in that case is that you have a higher material loss. So these are the reasons why you have that extra term of synergy, and there is a process to quantify that synergy. So how do we do that? So we have some standards that are prescribed by ASTM G119. And these standards tell us or give us the procedure or prescribe the procedure of how to quantify synergy. So this was the work done in my PhD, where we developed a test rig which is customized to quantify the synergy of any kind of metallic conducting material in possibly any environment sliding against an abrasive. So what was the test rig that was developed is this, as you see on your left. So we have a sample at the bottom, which is probably 8 mm in diameter and 10 mm in height. We have an abrasive paper at the bottom, which is a silicon carbide or alumina, whatever you can choose. And we have a corrosive medium and an electrochemically controlled environment. That means we have a reference electrode here which you can apply a desired potential, and you can stop the corrosion from happening or accelerate the corrosion from happening. This is because abrasion and corrosion work at different time scales. Corrosion may happen in years, but when you scratch a material against sand, there is immediate material removal. Therefore, to match those two time scales, we accelerate the process by applying an external current using these kind of setups of controlled electrochemical setups. So to just give you a brief video. So here we have this sample, and you can see that the arm moves from the left to right slowly upon an, let's say, imposed normal load. So we are abrading the sample, meanwhile corroding it. Of course, we can't have the contact area in field of view because it's not possible. So these are the parameters on which we tested. Yes, this is a lab scale test. This cannot be directly, let's say, extrapolated to a real scale environment, but this is a starting point of the studies of abrasion, corrosion, or the synergy of it to give some numbers and mean something. So these were the results. So we did see a negative synergy. As you see here, we did some tests in distilled water, which does not have any ions, definitely. So it does not have such corroding effects. The second one is an aqueous salt solution of 3.5 weight percentage NaCl. And this is, here we do not, why do we do this is because we want to keep the electrochemical interaction, let's say, controlled using a single salt. And here we do the tests from the water in the North Sea. So as you can see, the synergy is sometimes negative as well as sometimes positive. So these are the tests that we do where you see the greater or lesser material loss. So this is what we are going to do in the studies of the candidate materials in inSITE, and that's an ongoing process. And now I invite my colleague Manjunath to explain to us about the mechanical design. Thank you very much for this opportunity.
Good afternoon, everyone. A warm welcome to this mechanical design presentation. My colleague Kanaki, she explained about the phenomena, tribological phenomena happens between the materials when it comes in contact and how it's going to loss of material under different set of conditions. Here I'm going to talk more on mechanical design using her results and how we are going to design mechanical components in a better way. Now, for each and every applications, the conditions where we are going to introduce our components is different. In case of mining environment, like consider now earth mining environment or like underwater mining environment. In underwater mining environment, the major two challenges, the pressure housing or the materials which goes under high hydrostatic pressure. And the second one, the sealing the entire mechanical components is also a high challenge because of the O-rings that will go under extrusion into the clearance. In this project, we are responsible for mechanical housing design. And what are the challenges we are currently now in this situation? You can see here one example of mechanical housing. In this case, as a geologist or like mining companies, they want to go as much as deep. Extreme deep operation that creates a huge pressure on the housings that will try to buckle and fail the mechanical components. The second one, housing is to be so strong, stiff enough to withstand these kinds of pressure. Of course, the researchers and the geologists, they want to introduce the transparent windows to communicate with outside and to capture pictures and enclosures. It makes even more challenging environment to design the mechanical housings. As a design engineer, I'm going to give a brief introduction about how we are going to dimensionize or to calculate the dimensions of the mechanical components. If I want to calculate any mechanical component dimensions, we'll consider always factor of safety. Okay, we will play with the factor of safety. Oh, okay, what is the factor of safety? In this case, we'll always consider the yield stress as a main criteria to design any mechanical components. We'll divide the yield stress of any materials with factor of safety. For that, we are going to design or dimensionize the mechanical components. In this case, the marine applications mechanical housings, usually they'll consider 1.5 to 3 based upon his skills, design engineer skills. The pressure vessel is operating under a set of operating conditions like high pressure and the temperature, and the outside pressure is also fluctuating. In this case, considering 1.5 to 1.8 of factor of safety is a very good criteria. Now, if I consider 1.5 or 1.8, the hoop stresses and radial stresses, how it's going to generate and how it's going to distribute over the entire radius of the housing. As my colleague, she explained, she considered 3 different materials, one aluminum and titanium and SS316 stainless steel materials. Now consider a housing, and we will apply a hydrostatic pressure, a compressive load on the housings, and we will see the strength and the mechanical characteristics like the deflection and the buckling. In this case, we consider now 3 different materials, and we did 3 different simulations on FEM. Hydrostatic pressure we introduced on a housing, and we checked its stress and its deflection and its deformation. As I already mentioned, when operating depth it increases, of course the dimensions are going to be big, and we need a titanium materials or stainless steel materials based upon the operating depth. The next one is the end cap. The housing and the dimension is fit. Okay, how about end caps? I consider here 3 different end caps. Now you consider with first one, hemispherical head. Of course, it's a minimum plate thickness. If it's minimum plate thickness means minimum weight, minimum material cost, but the entire shape that makes the forming even more complex. In second criteria, you can see the starting it's a flat shape and with a dome. In this case, the thickness is twice than the first one. The material is more, and the forming it will be reduces. But the third one, in extreme high pressure conditions, these kinds of enclosures they'll use, less forming, and localized stresses may lead to the failure due to the brittle fracture. Regarding the seals, the elastomeric seals or O-rings are required here to arrest the leakages or water to enter inside the housings, to protect our cameras and optic fibers or photonics sensors inside the housing. A few examples of housings I'm going to show here. Depending upon the depth of operation, maximum of 2 km or 2000 meter, you can see here a figure, end cap designs and the selected O-rings and windows for the communication. Here they considered 2 different end caps, one a flat end caps and one more a domed end cap. For housing instrumentation, it need not to be a domed, a flat end caps is required just to connect or plug in our optic fibers into the housing. For housing, for the laser head, where we are going to fix a camera to capture images or to fix a laser head to communicate with the materials, In this case, one end is required transparent. To conclude this overall presentation, where we are in this inSITE project. Currently now, we're developing two housings, one for instrumentation model and one for laser head model. Currently, we selected a material and we set a dimensions of outer and inner diameters and the length. Still, the mounting details and electronics panel arrangements are pending. We're going to do that one in next month. And regarding the laser head also, it's same. We choose a transparent windows where we are going to fix it and which type of O-ring we are going to use and where we are going to fix a laser head, and for communications, how we are going to plug in or plug out the cables. To conclude overall this presentation, currently now we selected a material based on tribo-corrosion results, and we're continuously interacting with the team so that to make a robust housing for instrumentation model and for the laser head model. Thanks to management and organizing team to organize this physical event. We know this is a hard time to organize events like this in a physical, in this COVID situation. We really thanks to Anna for organizing this workshop. Thank you one and all.
Thank you, Manjunath and Kanaki. So, if any questions for?
Why not thinking in composites, even if you need a different configuration of the enclosure, or if you need to develop some different things? Why you go directly to the? I know. If I am electronic guy, if I need to do a job to put in my computer underwater, I go to the steel or titanium and so on. But since you in beginning talking polymers or composites,
yeah,
we don't do any test with composites.
Yes, I'm going to give a question answer to this one. Kanaki, okay. She is a material scientist.
Okay. So we first did a dive into the market to see what kind of materials are usually preferred based on the depth. And when we saw the potentials of composites, that was not readily available to, what kind of composites can be used, or because they are tailor-made. And we as a group are not fully expertise in composites, and that's a process in itself, or let's say it's a research in itself. So that's why we try to do this market study of what kind of readily available materials can be used for testing. So, yeah.
Thank you. Thank you.
Welcome.
So I have a question. I don't know which one of you should answer. So we see the material selection and also the mechanical design for the pressure housing.
Yes.
But as you showed there, the robots and the operating machines, they have other, for instance, the structures, the rigid structures, and the foams. So does your research also include optimization of these materials to endure more? And also, for instance, do you consider the mechanical design, hydrodynamics, does this play a role when it's flowing? It will be less abrasive or more? So do you have some research on this as well?
Actually, I'm working more into machine constructions. My entire PhD is into developing a machine to test bearings, a set of bearings under a high dynamic application, where we're going to apply axial load and dynamic load, axial load and radial load in a dynamic environment, and we're going from 0 to 3000 RPM. Considering all these three different parameters in a dynamic application, we are trying to play with first with analytical calculation, then we'll do a few simulations using available software platform, where we're going to optimize the things based on the end application. We'll consider those parameters and we introduce that one in a software. We try to optimize the things, dimensions based on stress, deflections. If I consider here in this case, if a robot, entire robot, if it's under 2000 meter, 2 kilometer down, in this case, hydrostatic stresses, how much it is going to influence, or how it is going to buckle the mechanical components. We're trying to do those things in a first platform, software platform. Then we will mimic a condition in a real environment. Then we'll optimize the dimensions based on that.
Okay, thank you. So any more questions? So let's thank again.
Yep.
So and we reached the end of the workshop. So we have come from, we started with the fundamentals in the first day. So you become aware of the possibilities of the LIBS technology. Jose and Salvatore show in detail the fundamentals and the applications. Then you saw the challenge that is to take this to the industry, but you saw that industry is there and is working on already putting the technology in very harsh environments, but still remains this challenge of quantification in mining environments. So you see all the dynamics and that is behind the rocks. And today you went into other details. And of course, I cannot forget, we went to Mars for a while to see how these technologies are already leaving the planet. And then today we see some more details on the complexity of samples and roadmaps to address this and business aspects, technical design. So we hope we give you a full, it's never full, but we give you a good overview of what it means to take new technologies to the market. So you have to have a challenge, you have to have the technology, you have to have many expertise. So as a researcher, I can say this is a very exciting place to be, to work with, you meet special people with different skills, with different views of the world. So this is very nice. So I hope, particularly for the students here, that you were a bit captivated by this aspect of the research. Me and Anna, we will get in touch with you to evaluate how much knowledge did you capture from here. And if you are kind to answer to this inquiry that we are going to send you, we will have a certification of attendance of the workshop. So this was organized in the scope of Project inSITE, funded by EIT Raw Materials. And in this contest, Eduardo is now going to say some words because EIT was kind to let this project gain visibility in a much broader European events. So I say goodbye for now and until next time, and I'll keep in touch. So you have our emails, our contacts. You can send manifestations of interest, questions. So, and thank you, Anna, for organizing this, and thank you again for all the kind researchers to take the effort to come here or send their presentations. So thank you very much.
Okay, it's time to close. It's time to finish and say goodbye. Not goodbye. I'm last obstacle between us and a port of honor in the lab. And the people only need to listen to me more 5 minutes and can taste some port, I suppose. It's true? Anna, the port honor is in the lab? Okay. I only go to just give you a quick overview about what's happening in the last week. We start in Brussels with in the black. This is this week. This is an event. A side event related with European EIT Raw Materials Week, and also the In Black have two side events. Okay, In Black is a side event, but you have a second level of side events. This is Mine Heritage and inSITE workshop, and we start in the Brussels. You start 1 week ago. You have an workshop it's also hybrid. Some people in the room with some speakers in the room and some other speakers in the world, and you start to talk about the deep sea monitoring and the impact assessment of the mining operations in deep sea. with participation with the Nicholas from EIT Raw Materials, Bramley from NOC, Young from GCA from Norway. This is, I forget the name, Hans from DAM. DAM is this is a mining company to want to go to the deep sea, and we start 1 week ago, Friday, in the last week with this workshop. And this you can see this is the team locally, but the most of people are remote. You see the distance of the people, not more 2 meters at least, and this is a very interesting workshop, and we are happy for it happening in Brussels. We put a flag in Brussels. It's not only in Porto. This is this idea is to start to create a Portugal Raw Materials Week. This year, start with us, the people from technology. Maybe next year we can join people from the other areas, from science, geology, and mining, more mining people instead to be only technological people. But we start. Let's see if next year, after the European Raw Materials Week, you can have a more broad or Portugal Raw Materials Week. But this is a good idea to have a Portugal week. Okay, and we are very proud to be a satellite event from European. And you can see this is highlighted in the site of the European Raw Materials Week. And and I know the people is not the people now is in world is the Portugal. This is a Portugal Raw Materials Week, but maybe some people are not here, and we are spread in Europe or in the world. Some people maybe from Australia, another from United States or South America or Africa. But this is a real event we are proud to organize. And we start with In the Black in Brussels, and we continue with Mine Heritage. The final meeting. This is a project supported by European EIT Raw Materials also, and we are proud to participate. And the meeting have also a hybrid session and also a field work. You can see this is the network of connections in the, I suppose, is the connections in the mine heritage. In the mine heritage is a beautiful image. No? This is software, the connection software. They give us the connection image, or is only random. Okay. And very important to highlight the field work also. They have a field work. They visit a gold mine in the old mine in Valongo. I need to thank the municipality of Valongo to support this visit, and the Alto Relevo it's very difficult to Speleology Association, and also the Professor Alexandre Lima, the Faculty of Science, the Porto University. They give us support in this visit, and this is very important for the people from Mine Heritage participation to also to see a field work. The people don't bring any gold from the mine. The gold is there, is rest there. It's only for the people see that, but this is a very enthusiastic and fantastic visit. Now the people, okay. Now we jump from inSITE. After Mine Heritage, the Raw Materials Week continue with inSITE, and the inSITE bring the people not only for the workshop but for internal meetings with the team of the inSITE, the visit of laboratory meetings with the steering committee and technical meetings, and this is a very hard work. And after that, we organized the inSITE workshop. They start yesterday with I forget some names, but clearly with Slava. Jose is on top, also do a presentation. I remember Stefano also do some, but the keynote speakers are Slavka and Jose, and today McLam, Amy McLam. Okay, and this is a very I don't sleep in this workshop 2 days. The topics is very diverse and very interesting. We start with basics, like with Jose, and we talk about the business to sell this equipment, to incorporate. This is a very interesting thing from science, from the basic to a product to the market, and we learn a lot because we learn some things in the basics. And in simultaneous, you understand this type of the market and the way to coming from research to a product with and the people like us like to do research with social impact. This research don't stay in the walls of the lab and now go out for one enterprise to scale up and have some commercialization of this product. And this is very important to say. This is the numbers. In the black, we start with 70 registrations, and the average in the Zoom meeting attendees are 30 people. Mine heritage is a 50 registration, but live stream, some people received links and appear. And are not registered but watch. And yesterday we reached the 212 people connect to the workshop, and this is amazing because the people spread the link, and the other people, friends and colleagues, appear and at least coming and see something. Maybe don't stay all the time in the workshop, but we have 212 different connections, and we are happy on that. Next year we go still with we go to continue with Wind Black 22. We don't know yet the format for Wind Black, but you can stay tuned. But maybe you have some surprise next year with different formats in some events, or maybe we also go to be maybe more intervention in some topics. Mining is a very hot topic with I don't know in English, polemic. I don't know polemic. Polemic, okay, that's polemic. And next year is some European calls go to happen, and also some directives. Maybe next year these regulations appear, and the people know the rules to go to the deep sea. The ISA are almost finished the regulations. And after that, the countries also must adopt or not adopt or changing the regulations to assess the deep sea. We go to provide some information, take on that, and we keep you informed about our next the program for the next year. And now I invite the people to visit virtually. For the people are here with us physically, but the people are behind the camera. I invite the people to visit now, a virtual visit to the Center of Robotics Systems. Please.
INESCTEC is a Portuguese institution that does research in various areas, and we here, I will show you some of our work in robotic systems and autonomous systems in multiple environments, sea, land and air. So we're going to show you a tour of some of our robots and some of our projects that we have been working on. We do here a set of developments in robotics and mobile robotics in particular, with an emphasis on underwater and aerial robotics. We also develop specific sensors for use in robotic systems, which is, for instance, the case of this camera for filming plankton and classifying plankton in the marine environment. So this is a microscopic camera that takes images of plankton and classifies in real time the plankton that is detected on the images. Like I've said, we work on aerial robotics, both from the fixed wing systems like this one, like Falcus, I can show you, which is, you see here an old prototype for a UAV, an unmanned aerial vehicle that was used for forest fire detection. So you notice in the belly of the plane, you see two black dots. That means that each one is a camera. One is a visible lights camera, conventional digital camera. The other is a near-infrared camera. And the combination of these two, the information from these two cameras on the onboard computer allows the robot to prevent in terms of detecting possible fire causes. So the robot will fly autonomously, and when it detects a starting fire in the images, it will send a message, for instance, by smartphone or traditionally to the fireman to check it out if it is a fire or not. We are developing a system that combines fixed wing. This is small white plane that combines fixed wing with rotary propellers like a drone. So it is possible to take off and land vertically and simultaneously have wings to have a large autonomy in terms of flight autonomy. We have been development. You saw initially one of the robots that we use it for aerial inspection and intervention with an hexacopter robot. I can show you another one, which is the Stork. So this is an example of one of the various multiple UAVs that were completely developed here on the lab. In this case, this robot was designed and belongs to a family of aerial robots that was used and is used for inspection of power utility assets like wind turbines or power lines or substations. So it was developed in part in cooperation with the Portuguese utility company, and we have other robots similar to this one that we developed for the power utility company in Portugal that now are being used routinely to get the inspection of these assets in the field. In the sea, we have robots that operate on the surface, which is the case, for instance, the Rouage autonomous surface vessel. So this is a 4-meter long electrically powered catamaran. So it's a robotic boat. You can see that it has a bridge with sensors, with GPS, radar, radio communications, thermographic cameras, visible lights cameras, cameras for image processing, for remote access. This is in the center box that we see here. In this case, there's the brain of the system, so all the embedded computers and the navigation systems. So those equipments, together with the batteries and the propulsion of the vehicle, allow this robot to operate at sea. So this is a robot that has been used in multiple projects and in multiple missions in the northern coast of Portugal. So it is possible to operate it in typical sea scenarios with waves reaching almost 2 meters height. We have used it either to do autonomous bathymetry, where you get a robotic boat that equipped with sonars can measure the profile of the sea bottom with high precision, because it has precise positioning and because it moves itself autonomously. So basically, the typical scenario of operations is to have this robot put it in a certain place. I will tell him, cover this area, and the robot will go in a long mount pattern and will take data, in this case, data from the bottom of the sea. We use it also in missions for testing bioremediation of hydrocarbonate spills, oil spills at sea, where we use the robot to deploy a cocktail of microbia that eats the hydrocarbons, and it is a local consortium of microbia in terms that is developed for each area of the region where it's supposed to be operated, and thus it can be useful in terms of helping contain pollution accidents at sea. This technology that we use in robotics is also used in mapping and navigation in tough scenarios where we don't have GPS and it's difficult to know precisely where we are. And this is important, for instance, which is the case of the MineHeritage project, where we use one system that has a set of, it has cameras, onboard computer, batteries, and LIDAR, and it is used inside galleries and mines, land-based mines and galleries, where we don't have GPS, to gather detailed 3D information and images from the inside of the mine in order to build a digital model, a digital twin of the environment. So this is like a robot, but without the actuation part, without the computer does not tell the system where to go. In this case, there's a human operator that carries the system in order to get the 3D modeling of the environment. This can be used inside mines, or it can be used in a different setup, for instance, in railway systems, in tunnels, in every place where we don't have GPS. So one example of this type of environment is the underwater one. So in underwater we don't have GPS, and so many of our underwater robots obviously need to navigate, and this is also an area where we develop technical skills and develop solutions in order for the robots to be able to know where they are. One example of one of these underwater robots in a very particular scenario is the UNEXMIN UX1 robot that we see here. So this is like an aluminum sphere, 60 centimeters wide, 112 kilograms of weight. And the objective of this robot is to explore flooded underground mines, so shafts and galleries. It can be mines that were being abandoned many years ago. It can be mines that are flooded and we want to explore certain parts of mines. So the operation is to operate in very constrained spaces. It can go up to 500 meters depth, and it was designed to operate, to make missions of about 5 hours, to have an autonomy of 5 hours of operation. This means that it can cover, depending on the velocity of the exploration, it can cover several kilometers, 4 or 5 kilometers of span. So this system is equipped with a set of cameras, with laser scanners, a custom developed laser-based system that is used to get very detailed 3D information of the environment, and sonar systems like a multi-beam sonar, a very compact multi-beam sonar that allow us to have a vision of the environment, even if the water is very turbid and the visibility is very bad, which happens in some mines. So this is a very tough scenario for a robot to operate, because many of the abandoned mines are full of debris. We don't know the state. They may have been collapses. the robot can be trapped. This is one of the reasons why it is in generally a sphere, around the sphere. The shape is around the sphere in order to try to avoid getting entangled in obstacles in this kind of environment. Just as a note, in Europe there are over 30,000 mines abandoned. So, and most of them are flooded with water, and some of them have economical value. They have been abandoned in 100 years, 200 years ago, and the state of these mines or information about this, both from the point of view of mineralogical aspects, even from the structural state, is something that is unknown in many cases. And these kind of systems can provide you a first image, a first knowledge of what's there in there. So what's the state of the mine, what's the resources that we can have some clue of the existence of these resources. Here it's another example of another autonomous underwater vehicle, which is IRIS. So this is a very small robot that is used at the sea. So it carries a set of cameras, sonars, small set of sonars, a general gripper. It was developed in a European project addressing the recovery of lost fishing gear at sea, because there is a huge part of, or a significant part of debris that is produced by lost fishing gear, and in many places it's relevant to have the possibility of know the state of the coastal areas and the fishing gear that is lost in the fishing activity in coastal zones. Obviously, is an autonomous robot, so basically we are all seeing the same concept, that we have a system that moves somehow. In this case, it has batteries and propellers, that has some set of sensors, sonars, cameras, and an onboard computer that allows it either to process the information and to decide by itself what to do. Obviously, when I say to decide by itself, we are talking about programming the robot to a certain task. In this case, I can program this robot to, okay, go to the bottom of the sea and try to find me the lost fishing gear that I lost yesterday. So this is the idea, and here the finding is the computer will try to process the information from the sonars and from the images and try to detect the target that I am expecting. For instance, in the case of Rouage, the programming was do this certain track and gather information about the profile of the bottom. A bigger AUV, it's EVA. So this is a 150 kilogram robot, also capable of operating at a relatively high depth, up to 500 meters depth. So this covers most of the continental, more than the continental shelf, so which is the area of the ocean that is with more impact for a human presence, with more economic impact. And the system that we see here, it was developed in the context of another European project that we participated for, ground-based underwater mining, which is basically to develop a system that could mine open pit mines, in this case not galleries and shafts, but lakes, quarries, where the idea is to develop a machine that can mine these environments without taking out the water. So basically, imagine an underwater excavator that excavates a rock and pumps the slurry to the surface. So this has a huge impact in terms of reduction of environmental concerns, like reduction of pollution, of noise. There is no problem with the dewatering of the water, because basically the water it stays in the same place. We only take out the raw materials that we need. And this robot was developed to support these operations. So in this project there was developed a robotic excavator. We were responsible here at INESCTEC for the perception and the navigation and localization of all the elements of the system, the excavator and all the other components of the system in the mine. And we were responsible for developing an autonomous underwater vehicle that would be capable of having a very high precision in terms of navigation. When it is at surface, it uses GPS to know where it is, but once it dives, it must navigate by itself without GPS. For that, it uses acoustics communications. It has onboard high precision inertial navigation systems and fuses all of this information in order to know where it is and also in order to accurately determine the shape and the profile of the underwater environment to help the mission. This can be done in this case initially on the land-based mining scenarios, but it can also be done, and we have been done indeed that also undersea. So basically it carries scanning sonars. This is a 3D ectoscope, which is a 3D multi-beam sonar that provides you one ping image with 3D information about what the robot it sees, even if the water is completely murky. It has cameras and also, like in the UNEXMIN robot, a set of lasers. If the water is clear, you can have a 3D precise measurement of distance at close range with laser-based information. We cannot see here, this is the foam, but inside we have two cylinders that house the electronics. So basically we have the computer inside of a metallic cylinder and a set of batteries that you can take out and change in the field. We have been using this at sea. And finally, to show you some of our robots, we have the robots for the deep sea. So basically the turtle, this is the first generation, the second generation, and the last one of the turtle landers. So these are robotic autonomous deep sea landers, where the idea is to combine a classical deep sea lander, which is a system that usually carries a weight that you drop in the sea, and it's supposed to take equipment to the sea bottom, stay there for extended periods of time typically, and then afterwards you have an acoustic release and you release the weight and the system comes to the surface with some flotation device. Here we combine this idea with the robotic system. So these robots have, for once, they have onboard computers, which is this in this case. We have here, like in all the robots, underwater robots that we see here, they have thrusters and batteries, so they are capable of moving themselves, but they are designed in order to stay at the sea bottom most of the time. So they are capable of dropping to the sea bottom, carrying a set of sensors, doing their mission at the sea bottom, and either by direct command, acoustic command from the surface, or by programming, simply for saying, stay 1 week or stay 1 month in this place, after that, take off and move to another place, 500 meters, 1 kilometer north. So because it has thrusters, the robot can locate itself to a new position. And in addition, it has a variable buoyancy system, so it can vary its buoyancy, so it can make itself lighter or flotating, and so it will emerge, it will float to the surface, or it can make itself heavy and it will fall to the bottom of the sea. This way, the operation of these type of systems, even big ones like Turtle 1, which is 1.5 tons, this is only 600 kilograms, even this kind of systems do not require the same type of man and ship resources for operation at the surface. So in terms of cranes, of operation, of tether management, the system doesn't have tether. So basically it carries its own energy. If it needs to communicate, it can communicate by acoustic communications at very low bandwidth, very limited communication capabilities. But if needed, the system by itself, it can come to the surface and talk via satellite at the surface with the host in the land, to controllers in the lab. This lab was designed, this area that we see here, with an open area, was designed to allow us to have flexibility in the development of robotic systems. even from the design, from the start of the building, of the construction of this building, we included a test tank because it was a crucial asset in the development of marine robotics, the possibility of having robots that can allow you, they have test conditions where you can put your robot in the tank. And so in this case, we have a marine test tank. The open area allows us also to have some kind of reconfigurability. Obviously, you see all of this in a somewhat confusion state where we got a lot of stuff packed up because we had 2 missions in the last 3 weeks. So basically, we are moving robots that are now, currently we have a robot, one of the UNEX mean successors or a similar robot, the UNEX robot, is currently in Ukraine because we were doing in the last week a mission in Ukraine for exploration of salt mines in the context of those mine exploring robots. We have also other systems that are now on an oceanographic campaign with the Portuguese Institute of Sea and Atmosphere in the Atlantic. So basically this is a lot of stuff that has been working real hard here in the last 2 weeks. But what I was saying is that this space allows us to have some reconfigurability. For instance, if you don't notice, but if you see in the images of the floor, you can see sometimes patches of green. And those patches of green that we can see on the floor mean that previously a big part of this lab had a football field. And the reason why I'm telling this is because we used to have a team of robotic soccer players. So basically we have a team of robots that participated in the World Championships of soccer robotics, where the robots should play robotic by themselves. Obviously, with the project that we currently have in the sea and in the air, we don't have the manpower or the resources to dedicate to that. So mainly the robots that you are seeing here are robots for the sea and air operations. And many of them in the marine environment because we have a very large experience in developing and operating robots specifically for the underwater environment. We also have a classical machine shop. We can show you a little bit, which is the milling machine, tools, large-scale 3D printer. We have a room with small-scale printers, which are crucial for the development of these systems. We also tightly integrate these developments here in the lab, in the INESCTEC research lab in robotics and autonomous systems, with classes that are taught in the Masters of Autonomous Systems in ISEP, in the Polytechnical School. So basically, the lab, the INESCTEC Robotics and Autonomous Systems lab is in the campus of the Polytechnic of Porto Engineering School, and the classes are given nearby. And inclusively in this building, we have two rooms for classes where the students that have classes there can interact with our research projects and participate here and do their work in close connection, which also gives them an edge in terms of knowledge that they gain, extra knowledge, and also introduces them, according to their capabilities and competencies, to the research environment. Looking from lastly, I will show you the test tank and one of our hyperbaric chambers. So we have here an hyperbaric chamber that is able to test our systems in waters, and that's pressure up to 2,000 meters. We are now getting a new one for 7,000 meters, so it's full ocean depth, allows us to have the test of systems to abyssal plane environments. Here you can see in the window of our test tank, we see a system that we developed for measurement of radioactive measurement. Is a radon sensor that is put in an underwater containment system. It's an autonomous system. You're seeing that it's currently working and measuring the the conditions in the test tank. This is a 5-meter depth test tank, 10 meters by 6 meters of operation. It has a movable crane with a passageway, and this test tank was considered initially in the design of the building because it was relevant to have immediate access to the water, so we can simply operate robots that are being developed, putting in the water and tested. Some of the equipment or the technologies that we work with, for instance, acoustics and underwater acoustics, are impossible to test without being in the water. Obviously, there are situations where it's difficult to test. The case of the ROAS autonomous vehicle, which has 4 meters long, it's really difficult to put it here. We already did it once in the beginning, but for that case, we need to have access to open water. It has also the possibility, it has controlled conditions, so we can put stuff in the water, we can have target for calibration of mission, of vision systems. We can have external tracking of the robots with cameras and other sensors. So basically it has a huge impact in terms of robotics development for the particular case of underwater robotics. In the case where we need spaces to test, obviously we can either test it in the Douro River in a very controlled conditions with calm waters, in the Leixões Harbor, in the harbor in Porto, and we also have a 19-meter long research vessel that can also support the operation of these systems and the deployment of these systems up to 60 miles of distance to the shore, so basically in the coastal area of Portugal. So this vessel allows us to deploy systems in the ocean, even at depths bigger than 2,000 or 3,000 meters. So we can operate these systems and deployment on the field and also support operations from the surface. The ship has a set of cranes and supporting facilities and onboard laboratory, and you can stay in the field for extended periods of time with a set of scientists on board, and engineers. So Mar Profundo, which is our research vessel, is also a key element in terms of infrastructure for us to develop this kind of advanced robotic systems to address the underwater scenario and the marine scenario and the ocean. And I think this I gave you a broad overview of some of the stuff that we did here in our lab, and my wish is that some of you that are seeing these images and this video will be able to see it in person here and accompany some of the developments that we are doing here. For me, it has been a pleasure to invite us to our research home, and I hope it has been at least interesting for you to attend and to see. Thank you.